Is it working now? Okay.
Right, so now our next speaker is Dionysios Anninos, talking about concrete calculables in quantum.
Thank you. I'm very grateful for the invitation and the opportunity to speak here. I've learned a lot so far in the workshop. And I wanted, so let me start with the title. So I chose the title Concrete Calculables in Quantum de Sitter, and I'm highlighting the two C's because it's connected to the cosmological constant question, which we've heard about. But if I had a different choice for the title after Juan's talk, I would call it There is no more to de Sitter space than its entropy. Anyhow, the work is based on collaboration with these wonderful people. And I'd like to highlight that in the audience we have Albert, who is an excellent postdoc at Harvard, and Beatrix Mullmann, who's an excellent postdoc at McGill. Okay, and they can tell you more about what I talk about. So, given time, I won't give you many details. You can find them in the papers, but the basic outline that I'd like to emphasize is some comments on the Euclidean picture of a de Sitter type of spacetime and why this is connected to some thermodynamic properties of the space. And then I'll quickly discuss some realizations of these calculations and ideas in lower dimensions, where we can write expressions to higher orders in the loops, for example. And finally, I'd like to make some more general comments regarding model building and a more general outlook of how these type of technical results can be used. Okay. So let's start by, because I don't assume people will be familiar, let's start just with the geometry and the Euclidean picture of de Sitter spacetimes. And so the Lorentzian global geometry of de Sitter universe, as you may be familiar, has this exponentially growing regions at very early times and very late times. We only observe late time growing behavior. And it's the spacetime governed by the presence of a positive vacuum energy, which seems to describe to some approximation the kind of behavior of spacetime in the current cosmological era. And because of this rather strong expansion, the traditional observables of flat space or anti-de Sitter space are not so easy to transport to this context. Nonetheless, at least in the weak coupling limit, there are some symmetries that govern the behavior of fields and fluctuations. It's a maximally symmetric space in its purest form, and the isometry group is this conformal group. In d+1 dimensions, it says so d+1,1. Now, from the point of view of an observer, and much to my pleasant surprise, we've seen this picture twice before in this workshop, in this conference. The spacetime is not viewed globally, but rather only a piece of the spacetime is observed, namely what's known as the static patch, which manifests only an SO1,1 times SOD subgroup of the full SOD+1,1 isometry group. And the metric of the spacetime in its purest form can be written entirely in a time-independent fashion, the expansion of spacetime being subsumed into the presence of a cosmological horizon. This horizon is not due to the contraction of space, but rather due to the expansion of space, which makes it curious and more difficult to understand than the counterpart for black holes. Nonetheless, there's a Hawking... It's a small fluctuation of the horizon. There's a Hawking temperature associated to this horizon, and also an entropy, and I think this is a particularly nice formula that involves all parameters, all constants of nature, including the basic parameter of cosmology, which is the vacuum energy itself. So, and it's a strikingly sharp formula in the context of a strikingly unsharp subject. And many people have tried to understand this formula from different points of view, and in fact I put here Schrödinger also, because Schrödinger worried about de Sitter space as early as 1956. Yeah. Okay, so far I discussed the Lorentzian structure of the spacetime, but we can also consider the Euclidean continuation, and there's a striking feature that both the global geometry as well as the static patch of this de Sitter spacetime continues to the compact space, which is just the Euclidean sphere, which is the maximally symmetric space with a compact isometry group of SOD plus 2. And the thermal, or at least the thermal behavior in the pure de Sitter rigid limit is exhibited by the requirement to periodically identify the Euclidean static patch time. Now, this is really only an approximation in the saddle point limit, because away from that, since there's no boundary and no place to put the Dirichlet boundary condition, even the size of the thermal circle fluctuates, and we have to path integrate over it, rendering this strikingly different from the black hole case. And here's the particular form of the analytic continuation. The one that cosmologists perhaps are more familiar with is the one that yields this Hartle-Hawking type instanton. But the one from the static patch also yields a full sphere, but you have to analytically continue a slightly different coordinate. Okay? So now we will really move to Euclidean picture, and I want you to have in mind this sphere. So, in addition to de Sitter, we can consider adding matter fields, and in this perturbative limit of space, we can organize the type of matter fields we can add in terms of unitary reducible representations of the de Sitter group, which can be labeled by something like a conformal weight and a spin associated to the rotation subgroup that's preserved in the static patch. For example, in 4 spacetime dimensions, for vanishing spin, we can have delta, the various representations which have been classified, such as what's known as the principal series representation, the complementary series, and discrete series representations. These physically correspond to different types of particles in the spacetime. And moreover, these representations can be characterized in more detail in terms of reduced characters of the group itself, such as the trace of e to the minus IHT, where H is the generator of SO1,1. And just to give you a concrete example, these are known for all particle types, and this will be useful later on. They take the following form, which is in fact different from the more familiar SO3,2 type character, because it involves things like the shadow, what we would call the shadow of the weight. And if we try to Fourier transform this is a formal equality because we have to regularize this, but one can do this in a symmetry preserving way. One can find a type of spectral density associated to the content of the character, which is this function rho of omega, which is computable. And the continuum, the fact that omega runs over the real line is a reflection of the fact that this is a non-compact subgroup of this isometry group. And just to give you a more physical picture of what this rho is, you can plot it, for example, in the case of, well, in general, but here's an example of DS2 for nu is equal to 2. And you see here 2 features. One is that in the complex omega plane, this is a meromorphic function whose poles have to do with the quasi-normal modes of the static patch. So Harishchandra's characters encoded already thermal nature of the static patch quite beautifully. And also you see that in the real axis of omega, it has resonant type behavior near the mass of the particle. So this is a strikingly rich object that follows from group theory that encodes already some features of the static patch. Now, I mentioned so far the entropy in the earlier slide. However, this is only an approximation to what is expected to be a series of corrections, and one would like a systematic way to understand how to compute this thing more carefully, in the hope that if we have more exact expressions for this entropy, we can start to anticipate what kind of microphysical theories may reproduce it. Okay, so this might be a strategy toward identifying interesting theories. And here I'd like to refer to the talk of Luca, which is an inspiring analog in the case of ADS2. Except that in the absence of a boundary, perhaps this is the sharpest and most clear calculable. I don't want to call it an observable, but we can call it a calculable in the context of quantum de Sitter. Okay. So the proposal of what this entropy is in the semi-classical expansion is that you have to sum over a certain variety of compact manifolds and path integrate against the Euclidean metric over the fields of your theory, including matter. Here I've integrated out the matter and I have just this function of the metric. And we can try to compute about the Euclidean saddle, which is just a round sphere, some fluctuations of this object, and see how far we can get and see whether we can identify the structure. So let me start by talking about the contribution to this functional just from matter fields propagating in a rigid Euclidean de Sitter space. And the result here, the goal of this calculation will be to express at the one loop level, but one can also discuss corrections, the path integral of matter fields on a sphere, which is something we've considered in many contexts in quantum field theory. Here I'd like to consider in this context, and attempt to write these results in the context, in terms of these quantities that I talked about before, namely the spectral density associated to this character, in a way that resembles a type of ideal gas trace. Okay? And in fact, as we showed in this somewhat long paper, one can get this type of results. Let me first report on spin 0 and spin 1/2 at one loop. The sphere path integral of these fields in any dimension for any mass, for any representation, can be written literally as an ideal gas type expression, which can moreover, and it's very convenient, be expressed in terms of the character as a function, this parameter t that I talked about. Just to give you a feel for the usefulness of this expression, things like the logarithmic divergences of these quantities that people compute often in the realm of functional determinants are encoded in a simple Taylor expansion at small t of these characters. So you can just generate all these coefficients that people have written many papers about just by looking at the tables of these characters for arbitrary representation. So I've split the example of spin 0 and spin 1/2 from higher spin, because when one tries to express the sphere path integral over more general representations that include spin in terms of these type of character formulas, one finds that there has to be a correction to this formula involving the character in d dimensions. And more concretely, I'm sorry, this is a picture of Boltzmann and this is a picture of Harishchandra. And more concretely, just to give you a flavor of the expression in d equals 3, what you have is a formula that looks almost the same as the formula over here, namely some sort of ideal gas-looking expression. However, there's a correction, so this is why it's a chi tilde, which involves removing from the character of the sort of four-dimensional, in this case, representation, a character that lives in a codimension 2. So it has a divergence which is codimension 2 compared to the codimension to the bulk character over here, and there's a coefficient that is sensitive to the spin, that in 4 dimensions is a universal coefficient that grows cubically in the spin. And also there's a minus sign, which may remind you of some early literature on this edge mode type theories, where you have to remove some type of degrees of freedom from the naive expression for entropy. And so this is, I should emphasize, this is an interesting minus sign that appears without necessarily the presence of fermions that you might use if you're after cancellations. And as I said before, the heat kernel coefficients appear in the small t expansion of chi. And moreover, this split between edge and bulk characters manifests itself in a numerical way. And if we can reproduce some early work on spin 1 by Cassinian, Huerta, and Dauger and others, where they expressed the coefficient of the logarithm in the entanglement entropy in terms of a piece that had to do with the mutual information and a piece which had to do with a more edge mode-like behavior. And it follows directly from this expression over here. So what I mentioned here was for massive spin fields, because although there's a similar type of expression for massless gauge fields, there are additional terms that appear, and let me just give you a flavor of that. In the case of four-dimensional general relativity, so at one loop, the expression of the partition function for GR, in addition to having these type of contributions, also has a term which is logarithmic in the entropy, which looks a lot like the Sen correction of a BPS black hole that Luca discussed in his talk, in fact, whose coefficient is rather universal and has to do with the dimension of the residual volume of the gauge group that's preserved when you fix the saddle to be the sphere itself. Okay, and then one can compute these things. And also, you get the tree-level Gibbons-Hawking entropy as the leading term. And then, in addition to these two logarithms, one being the more standard divergence in even dimensional spacetimes, and this over here, which is due to the residual volume of the gauge group, there is a phase in the way that we have computed this, which is subject to some debate in the literature, but we use the prescription most clear, started by Gibbons-Hawking and Perry and elaborated on by Polchinski to compute this. In the case of theories with additional massless higher spin gauge fields, this phase is modified and there could be combinations that yield no phase at all. Okay, so now that I discussed this general picture, and here the point of the results is that they hold for arbitrary dimensions, spin, representation, mass, whatnot, so that if you hand me a spectrum, I can, try to compute things. I just want to move on to cases where we can study these expressions, but beyond just the one-loop approximation using techniques that are not the standard perturbation theory. And in order to do that, one has to go, for the time being, one has to go down in the space-time dimensions. So this is the reason we are going down, in the hope to get all loop type expressions that we can hopefully compare to microphysical proposals for microphysical models. So let me start by discussing the case of three-dimensional general relativity with positive cosmological constant. Again, we will work in Euclidean signature. And in Euclidean signature, due to the relation at the classical or semi-classical level of this theory to Chern-Simons theory, one can re-express the model in terms of two SU2 gauge fields, which is a compact gauge groups, but at the cost of complexifying the Chern-Simons level. This is the price to pay for doing GR in the language of Chern-Simons. However, semi-classically, you may be able to use this picture to compute loops, particularly because there's no non-contractible cycles in the three spheres, so you might be able to analytically continue some of the well-known expressions in the literature. And here S naught, again, is the entropy of the cosmological horizon, which is a circle now in this context. And lambda is the coupling to something like a parity odd deformation of the Einstein-Lagrangian, which is allowed in 3 dimensions. And lifting from the literature of Chern-Simons theory, one can propose, and it would be nice to verify this from the metric point of view, an expression for the 3-sphere path integral at all loops in terms of this expansion of the semi-classical entropy of de Sitter. And so this is the expression which you can expand at large S naught, which is the semi-classical limit, and try to analyze these corrections. And so the point to make here is that if anyone tries to propose a model, a microphysical model for the de Sitter entropy in 3 dimensions, it would be perhaps wise if they try to reproduce some of these features, at least in its purest form. Now, at this point, I'd like to draw an imperfect analogy, because so far the model I discussed is topological and a little bit abstract. There's no local degrees of freedom in this theory, so you might wonder whether there's any sense to this talking about entropies and things like this. But I think there's a slightly imperfect but perhaps useful analogy related to pure Chern-Simons on a 3-sphere, whose 3-sphere partition function has been argued by various people to be related to something like a topological universal piece in the entanglement entropy when you consider the theory quantized on a spatial 2-sphere times time and you split the 2-sphere into 2 disks. This means I have 5 minutes? Thank you. And so even though the theory was featureless and had just a single state, it could be that there's some edge mode type interpretation. And in this Chern-Simons case, what you have is the entanglement of maximally mixed edge modes or infinite temperature that gives you exactly the expression of 3-sphere. It would be interesting to understand if such an analogy makes sense in 3D gravity. Now we go to 2 dimensions. And in 2 dimensions, one has even sharper results. However, one has to find models in 2 dimensions that permit saddles, which are given by the 2-sphere. And the problem is that the Einstein action is topological, and so you have to find more general theories. One way to do that is to couple, which was first observed by, Polchinski in this context, is to couple to 2D gravity in the presence of a positive cosmological constant that suppresses surfaces with large area, a CFT with large and positive central charge. And thanks to a lot of beautiful work in the late 80s and early 90s, I think, one can extract from this rather sharp expressions for the path integral at arbitrary genus, in fact. So this was originally work of Knisnik, Polyakov, Samonochikov, and many others. And so, for example, you have terms that are somewhat reminiscent of the higher dimensional analogs. However, in order to get a saddle and small fluctuations, you should really take the matter central charge to be large, because if not, you just have geometries that are fluctuating with order 1, but this can be done. And then it really does admit a 2-sphere saddle. And in the Weil gauge, in fact, this problem reduces to a type of problem in Liouville theory, which is a type of time lag or super time lag if you try to supersymmetrize the problem, which we are studying context. So what does the large central charge look like of this theory? Well, rather nicely, it has a large C expansion, which you can reproduce through loops, and the leading term reproduces, even though the total conformal anomaly of the theory is vanishing, the leading term is reproduced by the log of the cosmological constant to look like a Cardi-Calabrese type entropy, except it gets interesting corrections. And moreover, one can conjecture all loop expressions for this inspired by the DOZZ formula, which have very beautiful analytic structure. So again, this is a challenge for microphysics to try to reproduce or prove that doesn't make sense. So I just want to end with some remarks on model building and an outlook. And so if we look now for concrete models, we can use these kind of expressions to try to test spectra, towers of particles, which are perturbative, and see whether the totality of their contribution to the de Sitter entropy yields interesting expressions or UV cancellations. So one basic thing is these logarithms that are very universal, so it should be examined, and people have tried to examine these kind of things. Spectral constraints of C gravity in higher dimensions, and there's an inspiring paper of Klebanov and Giombi in the context of higher spin theory that tried to sum over an infinite tower of higher spin fields at one loop in Euclidean ADS and managed to reproduce a result compatible with the dual vector model. So could you have higher spin spectra, which are models of de Sitter that seem to make some sense, where you sum over all higher spin fields and get interesting cancellations? So far, in fact, for higher than 5 dimensions, this doesn't seem to be the case, and there seems to be strong infrared issues. And there could also be other microphysical models inspired, for example, by SYK and other contexts. Before I end the talk, how much time do I have? 1 minute? Yeah, let me just quickly make some comments about the Lorentzian picture, just because the world is Lorentzian. So there are some unusual but important Lorentzian physics that any model building approaches is to reproduce from a microphysical point of view, namely pulses of energy in de Sitter have the effect, and this is also discussed by Shira's talk, have the effect of stretching the Penrose diagram of de Sitter in a vertical way, allowing for signals that were previously out of causal contact. Geodesics connecting the two sides tend to become complex when you push the 2 points further in the future, which is different from the case of black holes. And also there are interesting oscillatory behaviors due to the slightly different nature of quasi-normal modes in de Sitter that perhaps mimic some features in theories with energy gaps like BPS cases. Okay, so having said that, I think I'm out of time. I'm still waiting for these 2 bells. Oh. Okay. So there's a need for, let me just summarize, there's a need for sharp calculables at the quantum level to bring us a step closer to clarifying interesting quantities, such as what is this entropy, or if it is an entropy at all. This seems to be a very sharp calculable, or perhaps they will provide concrete inconsistencies that allow us, to clarify whether we should think about the problem in a completely different way. So here's a picture of a whirl line and a black hole. Okay, and thank you for your time.
Questions?
Hey, so you mentioned at the end of your talk this calculation by Giambi and Klebanov of the one-loop sphere free energy.
Could you? I'm really sorry, but with the mask, I can't hear very well what you're saying.
Can you hear better now?
A little bit, yeah.
So you mentioned at the end of the talk this one-loop sphere free energy calculation by Giambi and Klebanov. So I just wanted to point out that that calculation is invalid because, I mean, of course, you cannot compute anything at one loop without knowing the action. And when they did the calculation, they did not know the action for higher spin gravity. And so the way they were able to do it is that they assumed a certain canonical kinetic term, and they got an answer which didn't actually match free theory. They had to do some kind of shift. And then when they did that calculation in other contexts involving fermions, their answer just had no relation to the expected answer.
So, okay, thank you.
Yeah.
So I wish Igor or Simon were here to defend that point, but I should refer to perhaps an update on that story from a paper of Simo-san that does this calculation in a group theoretic way that sums over characters. Yes, under the assumption that the quadratic action of these fields is the standard Front-style action. So let me rephrase the observation in the following way. Take a tower of higher spin fields governed by the Front-style action without committing to anything else and sum over their contribution. It turns out that the sum of these infinite characters of 4D ADS subsumes itself into a 3D character. So you can at least take that. That's a mathematical fact.
Okay, yeah, but I just want to point out that we actually know the action now for higher spin gravity, and we know now that the kinetic term is quartic in derivatives and not
okay, so
quadratic.
Then you can do, with respect to that action, a version of this calculation, and you should get something compatible with the ON model, if the conjecture is true.
Four-dimensional gravity, pure gravity, I find very fascinating that the partition function has a negative sign. Because I would have thought that this is the inner product of half spheres.
Yeah, thank you for the question. I also find it puzzling, and if anyone doesn't find it puzzling, please let Juan or me know. So I think, I'm not sure I agree with the fact that it's an inner product, because, and this is a comment already in the Hartle-Hawking paper, actually, that in the Wheeler-DeWitt theory, it's like a Klein-Gordon norm, and you have to choose a hypersurface in the space of superspace. And when you integrate over all configurations on the sphere, it's as if you're also integrating over the scale factor. And I'm a little worried that you have to impose some additional constraint to call this thing an inner product. Moreover, the Klein-Gordon norm, it doesn't have a definite sign. Here, I really don't want to interpret this as an inner product or as a thermodynamics. I just want to compute it. But I agree with the comment, the spirit of the comment. Sorry. Is the microphone on, Andy?
Yeah, should be on.
Can you hear?
I can hear you now.
Yeah. I just want to ask about a funny and confusing factor of two. So you computed a partition function in which you integrated, I think, over the unitary principal series, and then you said it was it could be written in a product form with the poles of the quasi-normal modes.
Yeah.
But if I remember correctly, the complete set of quasi-normal modes for de Sitter space come in two kinds, one for the northern diamond and one for the southern diamond. Now, do you include both of those?
Yeah, it's these two towers over here.
Right. So when you say the quasi-normal modes of the static patch, you mean two sets, one for the
A single
northern...
static, sorry, just to be clear, a single static patch already has these two towers.
Well, then there's four. There's another
So it's just
set.
two then.
So just half of the quasi-normal modes.
I believe in your terminology would be half of them.
Even though it's all of de Sitter space.
No, this is just a static patch. Oh, this is reflected, sorry, to be clear, this is reflected, and I'll be done, in the fact that here I'm only integrating over positive omega, whereas the character you had to integrate over the whole real line. It's related to that.
I see.
Yeah.
Okay, thank you.
Thank you.
Right, I think we're out of time, so let's thank.
Thank you.